I think I mentioned this on Wednesday, but we're going to kind of go rather quickly through the next few sections here because we covered them last Wednesday in lab. But I do want to touch on them again because they are very important. And it's always good to come back and review these things. So significant figures, right, we covered these, I think even in lecture maybe. But all non-zero digits are significant. Interior zeros, so those between two non-zero digits, those are significant. Trailing zeros are significant, but only when there's a written decimal place. And then leading zeros, which I think is on the next slide, never significant. If it comes before the first non-zero number, going left or right, it's not significant. Even if there's a decimal. Doesn't matter, right? It's before the first non-zero number. So it's the difference between leading zeros and trailing zeros. So if there were zeros after this 5, they would be significant. Because again, written decimal point and coming after a non-zero number. We talked a little bit about discrete or exact numbers, which have unlimited significant figures. So it's like if you're counting, a number of pennies or a number of people, a number of desks, right? You can look at desks and see that there are exactly 2 of them, or people. So those, because there's not like a continuous, you can't if we could look at this desk more closely, we wouldn't find that it was 1.1 desks. It would still just be 1 desk. Whereas if you're trying to measure how long something is, you can keep zooming in and get a better and better ruler to measure it more and more finely, or a better and better scale to get the mass more accurately. So we did those. And then significant figures and calculations. Most of the time, we're going to be just using the rules for multiplication and division. And in any calculation, you only round the final answer. So as much as possible, you want to keep the whole number. Actually, maybe I'll remember to do this in lab. You can on another reason I love the TI-36X Pro, and it's the recommended calculator, is because it has a function for storing numbers. So let's say you do a bunch of separate calculations and you want to keep all those, but you don't want to write the whole thing down and then type it back into your calculator. You can hit store, and then there's this button here that has like X, Y, Z, T, A, B, C, D. Those are variables that you can store numbers as. So that helps prevent that rounding and rounding errors. But for multiplication and division, like I said, this is what we're going to be doing most of the time. You're going to be using the fewest significant figures in those steps. And most of the time, it's going to be the number that you start with, because you're converting that into another unit. And all of the conversion factors will be either defined quantities, or they'll have more sig figs than your starting number. We talked about rounding, right? If we want 2 sig figs, for example here, the next number that comes after it is 4 or less, then we just drop everything after our last significant digit. If it's 5 or more, then we would round up, so here it's 7, 2.37, and so we round that 3 up to a 4. And again, only do that at the last step for the answer that you report. So if you have a report sheet, especially for labs, which I guess in this class we'll do, Wednesday will be our first experiment. Anything that goes for a reported quantity. So it says, what is the mass of the metal cylinder? That number should be rounded to the correct number of sig figs. If you go on and you use that number in a calculation later, make sure you have the whole number written out so you can use the whole number for your calculation and not the rounded number. I'll try to remember to rehash that when we get to lab. Yeah, okay, so that's kind of where we left off. I think we might have done some examples in lecture. I don't remember for sure, but let's do these examples real quick. So we're doing multiplication and division. So if we have this string of numbers, how many sig figs does 1.10 have? It would be 3, because non-zero numbers and then a trailing 0 with a written decimal point. And then 0.512 is 3 again. 1.301 is 4 sig figs. Got an interior 0 on that one. And then 0.005 is only 1 sig fig. And then 3.4, 2 sig figs. Right, so how many sig figs is our final answer going to have? 1. Yeah, just 1 because it's the smallest number of sig figs. Type this in. And assuming that I typed everything incorrectly, 0.001, actually the whole number would be 0.77534. So if you're going to use this in a calculation later, that's the whole number that you would use, but the reported number would be 0.001. How about for this next one? What's our smallest number of sig figs? Yeah, 3. So this one has 3 sig figs. This one is 6. And this is 4. So 4.562 times 3.9987 divided by 89.5. So whole number again here would be 0.0238220004. But we want 3 sig figs for our final answer, so it'll be 204. Because these are our 3 sig figs that we're going to keep. The next digit after the 3 is 8, so we round it up to 4. Addition and subtraction will come up, specifically in a couple equations. Specifically in a couple equations it'll come up. When we're doing addition or subtraction, the result carries the same number of decimal places as the quantity carrying the fewest decimal places. And this is where the distinction, I want to highlight this, is that it's decimal places and not sig figs now. So for this first example, if we look at just the places, and for these calculations it can be easier to write them stacked, right, like you would to do them by hand, because then you can see all the decimal places lined up. But 5.74, 2 decimal places. The rest of those have 3 decimal places, right? So it's how many numbers come after the decimal. So 5.74 plus 0.823 plus 2.651. And that's 9.214 would be, again, the whole number, but we would round it to 9.21. And I think, well, I'll do this next example first. How many decimal places will the answer of this calculation have? 1. Just 1, right? Because 4.8 has 1 decimal place. So 4.8 minus 3.965, that's 0.835. And then our final answer, or reported answer, would be 0.8. It's
do times 10 or whatever.
Yeah. It's so the rule of thumb that I've been giving everybody, and maybe I should change this a little bit, is really the rule of thumb that I've been giving is if it's greater than 10 or if it's less than 0.1, then you use scientific notation. So this number is greater than 0.1, but it's less than 10, so we can leave it. This number is, again, less than 10, greater than 0.1, so it falls in that range of where we don't really need to convert it into scientific notation. But it is just a rule of thumb. So you could write this answer here as 8 times 10 to the negative 1. Those are the same number. But scientific notation is used either to make numbers more convenient to write or to read, or to better compare different numbers. So if I was looking at 0.000359 and 0.0000478, for example. So I'm looking at these two numbers. Is it easier to compare them like this, or if I write it out as 3.59 times 10 to the negative 4 and 0.478 times 10 to the negative 4? Yeah, I think it's easier to do the scientific notation, especially if they're not written on top of each other like this. So you can see that one is actually 10 times smaller than the other. If they're written side by side, then you have to count those zeros. But when we look at them in scientific notation, and you'll notice here I broke one of my other rules of thumb, which is that you use the scientific notation to write your number so that the decimal portion, this first portion, is between 1 and 10. But the reason that I didn't do that here is because I want to compare these two numbers. So we can use scientific notation to sort of put them, to show that they're relative to one another. So now we can look at a glance and we can say that, oh, this is 0.478 and this is 3.59, and we can just compare really the decimal portions because they're both times 10 to the negative 4. So decimal's been shifted over the same for both of them.
So if you would have shifted decimal over to after the 4 of 4.78 and changed your negative 4 to negative 5, would the answer still be the same?
It is still the same answer. But now at a glance, when you look at these numbers, it looks like 5.7, or the 4.78 is bigger than 3.59, but it's actually smaller because it's times 10 to the negative 5 instead of times 10 to the negative 4. So scientific notation is really a tool so that you can present your data in the best way possible.
The reason I'm asking because I went to tutoring last week, and if you go back to your other slide, you know how it says that the trailing, you see like the second one, or first and second, where it has all those numbers at the end, they're all significant figures. So they said if they're significant figures, you should do the scientific notation because you want to show that they're counted for.
Yes.
Does that make sense?
Yes, I understand what you're saying, and it's especially important for large numbers. Here, these aren't significant because we did this whole calculation here. And so it's the calculation and the numbers that go into the calculation that determine which digits of the answer are going to be significant. But if we had just taken this number and like that's what we read off of our instrument, and our instrument reads out to that many decimal places, then yes, all of those would be significant, and it would be 1.077534 times 10 to the negative 3. Does that make sense? Still missing it.
Does it matter, like if it's mass or volume or whatever? Maybe that would, no? Okay.
No.
Okay.
So,
You're saying like this is a whole already. It's not like it can be 0 point whatever.
right.
Because it's a whole.
But if we went to get the mass of that desk, then we can keep getting better and better scales, and it would give us more and more decimals, even if the previous decimals were the same. So
if I were to write it differently with the scientific notation, would I get it marked wrong?
So are you asking if 1 times 10 to the negative 3 here would be the same? That would be the same.
Okay.
As long as you only have as many significant figures in the scientific notation. Yeah. Those are the same number. Yeah, so I should have converted that one into scientific notation. Yeah. Okay. So addition and subtraction. Wanted to point out too that if we had numbers like this, those previous zeros aren't significant, but they are still the number of decimal places. So if we added these together, maybe I can move this out of the way. Oops. So if we add these two numbers together, how many decimal places do we keep? Yeah, however many are in this top one. Yeah, 1, 2, 3, 4, 5, 6, because that's one fewer decimal place than the bottom one, which has 7. And here's another place where it can be useful to put them into scientific notation, but it doesn't change the number of decimal places. We can't really add these two together directly because, again, this times 10 to the negative 5 and times 10 to the negative 4, those are different. If it's the same, then we can add them together, and this still has one fewer decimal place than this number does. So this would be 0.000, I can't do that in my head. Uh, 3, 1, 1, 2. We're only keeping 6 decimal places here. 5, 6. So this will be either, well, this is not in scientific notation, but because this number is so small, it's going to be easier to write it in scientific notation. So that would be the final answer that I'm looking for. Just know that scientific notation doesn't change the quantity of the number. It just changes how we write it. All right, we have more examples for this. Yeah, so one of the weird things that can happen with addition and subtraction is you can actually lose significant figures. So for example, if we have these two numbers, 28.02 minus 27.99, how many decimal places are we going to have? 2 decimal places. And that's what's going to determine how many significant figures our answer has. So 28.02 minus 27.99 is going to be 0.03. And we're only keeping 2 decimal places. We should write this 3 times 10 to the negative 2. So now we went from having 4 sig figs in both of our answers, or in both of our numbers before, to just 1 sig fig in the answer from this one calculation. So you can lose significant figures, and that's why there are some labs where it specifically says we got actually kind of 3 different types of balances in the lab. In the back of the lab, there's the lab balances, and they're decent. Some of them go 2 decimal places, some of them go 3. But in the back, in the stockroom, we have the analytical balances, and they have 4 decimal places. So there are going to be some labs where you need to use those because you're going to be subtracting 2 numbers that are going to be very close together potentially, and you don't want to end up with just 1 sig fig. Because if we had used balances here that had 4 decimal places, we could still potentially have 3 sig figs from this. Okay. So we're adding and subtracting. And remember, this is now adding, subtracting, so it's decimal places, not sig figs, that we're looking at. So how many decimal places does 2.18 have? 2 decimal places. I guess I'll write DP for decimal places instead of SF. And then for this next number, 5.621, 3 decimal places, and 4 decimal places, and then just 1 decimal place. So when you're doing calculations like this, I don't necessarily expect to see every time that you write out the number of decimal places, but if that helps you, by all means, do it. So if we add these together, or we'll add and subtract, there's a combination of functions here. 2.18 plus 5.621 plus 1.5870 minus 1.8. We're going to get, as the whole number here, 7.588, but our smallest number of decimal places is 1. So this will be 7.6.
So that's how we would do it on the calculator, is just straight across and then take the answer and then round it to find.
Mm-hmm. The only time you can't do that, and we'll get to it, and I think we did talk about it on Wednesday, but if you're mixing addition, subtraction, multiplication, division,
Then you have to use the please excuse my situation.
yeah, then you got to do that, and then at each step you have to figure out how many sig figs you keep. But we've got an example of that too. Okay, so this next one, fewest number of decimal places. So 2 decimal places here, 3, 3. So then 7.876 minus 0.56 plus 123.792. And for addition and subtraction, the order doesn't matter. So 131.108. And we're only keeping 2 decimal places. So it's 131.11. Be the final answer. So I think individually, not too difficult. When you combine them, it gets a little trickier. I believe that's what the next slide is. Yeah. So it says, do steps in parentheses first. That's the please excuse my dear Aunt Sally, parentheses, exponents, multiplication, division, addition, subtraction, in that order. So then you determine the correct number of sig figs from your intermediate answer without rounding. Do the remaining steps, and then round the final answer considering the number of significant figures in the intermediate answer. So we'll see what that looks like. All right, so if we have here, we've got multiplication and we have subtraction. And so because the subtraction is in the parentheses, we're going to do that part first. So 720 or 782. 72.3 minus 451.88. So that intermediate answer is going to be 330.42. Okay, so for our intermediate answer though, how many sig figs?
4.
Yes, 4, because we did the subtraction, so we're going to keep the smallest number of decimal places. And if this helps, think about like, okay, if I was going to report this intermediate as a final answer, where would I round it? At this 4. So so we're going to keep that one, and then everything before that will also be kept as significant. But now we keep that whole number. So I'm going to use the whole 330.42, multiply that by 3.897, and the result of that is going to be 1287.64674. Now, how many sig figs of that do I keep? Sig figs. So we're doing multiplication or division, so smallest number of sig figs. Yeah. And so here, this one only counts as 4 sig figs because that's all we would have kept from the previous step. So that 2 is not significant, but is still important to add into the answer to avoid rounding errors. So we're only going to keep 4 of these. So, right, 1,288, because that, I don't want to put an underline, but that's going to round up. And so this should be 1.288 times 10 to the 3. All right, on this next one,
So we would have just left the 1, 2, 8, 8, it would have been wrong.
yes, I would have taken off half a point because it should be in scientific notation there. Yeah. Now, it's still the same number, and it does still reflect the correct number of sig figs, but I am trying to get you to use scientific notation, so that's why. It's just because I'm telling you to write everything in scientific notation that's greater than 10. All right, so for B, what's the result of this? So we're going to start in the parentheses again. So if I do 4.58 divided by 1.239, how many sig figs is our answer going to have? Yeah, 3 sig figs. Because 4.58 has 3 sig figs, 1.239 has 4 sig figs. So we're doing division here. We want the smallest number of sig figs. 6, 9, 6, 5, 2, 9, 4, 5, 9. That's a long one. 0.578. And like I did on this first problem, I'm going to mark with underline. I'm going to underline all the digits that are significant, so that in my next step, I know which ones are significant without having to go back and do it all over again, or think about the sig figs again. So we're going to take that number minus 0.578, and that's going to be 3.118529.459. And so how many decimal places now do I keep? So this one has 3, and then this one has 2 significant decimal places. So the rest of these aren't going to count for that, because if we had just done this part, right, we would have rounded all of that off. So just 2. So this will be 3.12. Right. Yeah.
Does that have to be in scientific notation, or is that okay to just leave it like that?
So if we wanted to write 3.12 as scientific notation, how would we do that?
3.2 times 10 to the power of the number you 2?
Well, we're not moving the decimal place anywhere, because it's already a number between 1 and 10. So if it'd be 3.2 times 10 to the 0, because then 10 raised to the 0 power, well, anything raised to the 0 power is 1. So there's no reason to write any of that extra stuff. So yeah, 3.12 would be the final answer there.
Where would I be able to find this? Is it on YouTube on the syllabus? I'm trying to find it.
Oh, like the video?
Yeah, or yeah,
Like
your,
the link to your
lectures
Yeah, it's on the syllabus.
on the YouTube link.
Uh-huh. Yeah, if you click that YouTube link. If the YouTube link doesn't work, let me know, and I'll put a new link up. Or I can post another link somewhere else, too. Yeah. You can also just search my name on YouTube.
Well, but aren't you uploading the slides that we're talking about right now?
I haven't been, but I can. That's the thing that I always forget to do.
Well, you uploaded the ones from last week. I watched them.
Yeah.
The videos are up,
Yeah.
but not just like the annotated slides.
Oh.
Yeah. Because I don't know why, for some reason, the videos I can get uploaded, the annotated slides I always forget to do, which is why I haven't promised to do it. I can try to do that, though.
I would like to print that instead of writing it all down and just.
Oh, you mean just like the blank slides?
Yeah, that we're doing right now. Yeah.
Oh, those are on there.
Slides.
Those are,
Yeah,
they are under,
in the syllabus, right?
no, they're
Mm.
under the modules where it says like your,
It's like overview for chapter 1 and 2.
it's the handout. So there's like the slides, like you can look through one by one, and then the handout, you put them like this. And I just
Yeah, if you go, let me try this real quick. Okay, so here's the canvas. So if you go to modules, and then if you scroll down to like chapter 1 and 2, preview chapter 1 and 2. Sorry, I should have pointed this out. It's got all the different, these are actually great notes for, usually when I write exams, I use these objectives. So it's like, these are the things you were supposed to have learned. I'll pick some of those because we don't have time to do all of them, and use those to write exams. But if you scroll all the way down here, there are the PowerPoint slides and handouts. So the handout version, and I would recommend downloading them and then printing them, and not trying to print like the browser windows. This is the one that has 6 on a page. And then,
If you try to do that, it just prints out like your whole entire like screen that you have up there.
yeah, and it looks pretty rough.
Yeah, I wasted a bunch of my ink. So
Yeah, all right, well, my computer is sad.
So there's like when you go in there, there's like a over on the side. See where it says download at the top?
Yeah,
Oh,
I
yeah.
prefer to print it like that, like the whole page.
You can do that too. Yeah, there's 2 versions.
It's like 60 pages.
Yeah, it's,
Do I just print front and back?
right, yeah. Or you could do 2 to a page, or, okay. Got to move on though. All right, so we also talked about units, right? We talked about the metric system, the importance of units. I do like the sentence. When my son was 7, he walked 3, and when he was 4, he could throw his baseball 8 and tell us that his school was 5 away. What does that sentence mean? Now, you can use some context clues and say it's like, okay, my son was 7, probably not 7 years, I know he could be 7 years old and walked 3 miles, or he could be 7 months old and walked 3 steps, or really anything. And when he was 4, again, years probably, about 4-month-olds throwing baseballs, but threw his baseball 8 what? Feet, miles, houses, right? So the units are super important for letting other people know what your numbers mean. Again, this comes back to that first slide for this chapter where they used the wrong units when they were trying to like redirect the satellite and crashed it into Mars on accident. So, or if you're, working like as a nurse or as a doctor or something, and you're prescribing like a potassium drip or something, you need to make sure you get those units right, otherwise you're going to kill somebody. So yeah, the 2 most common systems are the English system, the metric system. English system is the one that we're familiar with. The metric system is the one that we will be using almost exclusively in this class, unless it's a question asking you to convert units. This table, I think, is actually super, super useful because while in the English system, right, in the English system for the weight of something, you can have ounces, you could have pounds, you could have tons, you could have stone, which is, I think a stone is 12 pounds or something, 14 pounds, right? So there's all these different, completely different names for different like levels of weight. In the metric system, they're all based on the same thing. So if you have a length, it's going to be in meters, or like we talked about the metric prefixes, it'll be centimeters, kilometers. Those are all just modifications to the length of a meter. It's either 1 meter, or it's 10 meters, or it's 100 meters, or it's 1,000 meters. And that's what a kilometer is. A kilometer is 1,000 meters. And then those same prefixes can be used for length, meters, or mass, which is grams. Here, the kilogram is what we define the gram based on, but the smallest unit, the base unit, is a gram. And then time will be in seconds, and temperature is actually in Kelvin, which we haven't talked about Kelvin yet, but we'll get there. The other nice thing, or the other important thing, I should say, about metric units is they're based on universal constants. So like the meter is defined as the distance that light travels in a vacuum in 1/299,792,458 seconds, 1/158 of a second, right? So that is the definition of the meter. So we can go back with the correct instrumentation, measure how far that light travels, and we could redefine the meter and have the same units as, let's say like civilization collapses, and in the future they discover like this is what we used. They could be like, they could go and they could get that exact same measurement without having somebody around to tell them. Actually, interesting anecdote about that, about units being like rediscoverable. The Saturn V rocket, which is I think the rocket that first sent people to the moon, we can't build that rocket anymore because the notes and the knowledge of the engineers who built it are lost. And we have the schematics. We know what it should look like. But there were so many little things that they had to adjust and fine-tune in super small ways that we can't reproduce it now. Because those engineers have either died, or they didn't write down good enough notes, or it's just gone. And sure, we could figure it out, but we've built more powerful rockets now. But yeah, that technology is lost because it's not reproducible. But using units like this makes it reproducible. The kilogram is actually, I should change the slide because this has changed. The base unit of mass is the kilogram, but a kilogram, right, kilo means 1,000, so a kilogram is 1,000 grams. It's an easier mass to work with. It's slightly larger than 2 pounds, 2.2 pounds. It used to be based on an actual piece of metal that was kept just like this, and that was the definition of the kilogram. However much that chunk of metal weighed was what a kilogram was. Now, that's not very reproducible. If in the future civilization collapses and they want to reproduce the kilogram, they'd have to have this. So it's been redefined based on some crazy math. So if you want to look that up, it's on Wikipedia. Oh yeah, the kilogram is a measure of mass, which is different from weight. So on Earth, mass and weight are the same thing. Our weight is how much gravity is pulling us down towards Earth. But if you went to the moon, you would weigh less, but you would still have the same mass. Because mass is a measure of how much matter you have, or how much matter something has. So those are different. For reference, a nickel has a mass of about 5 grams. 1 milliliter of water is 1 gram. So the base unit of time is the second. This is another one that's cool. You've heard of atomic clocks. Atomic clocks are using cesium-133, and they're measuring essentially the vibration of that cesium-133. So, every 9 billion vibrations of that, or radiation emissions, that is 1 second. And that's how we've defined it. So the SI system, we talked about this, prefix multipliers. And the easiest way to do it is to put the prefix multiplier on put 1, if you're trying to define one of these unit conversions, put the 1 with the unit that has the prefix. Then the prefix tells you how many of the base unit that is. So this is 1 kilogram. Kilo means 1,000. So this is 1,000 grams. So this would be, one, in this case, meters. It's the same thing. 1,000. So 1 kilometer is 1/1,000 meters, not 1,000th. Units really are another thing, kind of like scientific notation. So we can use units that are sort of on the scale of the things that we're measuring. We wouldn't use kilograms to measure pennies, right? The mass of pennies, and we wouldn't use kilometers to measure how far it is to walk from this room to my office, or to measure the size of the room. Kilometers are way too big. We would use meters instead, or we'd use grams to measure the mass of a penny. And a lot of times those units will be given to you. It's just use these units, or it's the units that come off of the instrument that you're using to measure. So this is the table. I think I mentioned this table in lab, but this is the table of all of the prefixes. So if you want to reference this is also a universal thing. These are the standard prefixes. So you can Google metric prefix table and get something just like this. Okay, so if we wanted to express the dimensions of a poliovirus, which units would be the most convenient? So we're looking at, and I'll write this, I'm going to go back, but 2.8 times 10, or the negative 8, yeah, negative 8. So if it's 2.8 times 10 to the negative 8 meters, which units would be more convenient than that? Yeah, micrometer puts us at times 10 to the negative 6. It might even be better to use times 10 to the negative 9, so a nanometer. So if we wanted to convert meters into nanometers, our conversion factor over here, I'm going to write it. So 1 nanometer would be 1 times 10 to the negative 9 meters. So you see I pulled that 1 times 10 to the negative 9 right off of here. So 1 nanometer is 1 billionth of a meter. So that's why I wrote this is 1 billionth. So we can convert this. We want to get rid of the units of meter, so put those on the bottom. We want units of nanometer on top. So 1 nanometer, 1 times 10 to the negative 9 meters on the bottom. So 2.8 e to the negative 8 divided by 1 e to the negative 9. So now this would be 28 nanometers. So nanometer would be the most convenient. So generally you want to pick, if you're picking units like this, you want to pick a unit that is smaller than the thing that you're measuring. Like 1 step smaller. That way you get whole numbers. So let me do this too, actually. So this would be 28 nanometers, which we could write as 2.8 times 10 to the 1. If we had used, I guess the other one we have here is micrometers. If we had used micrometers, this would have been 2.8 times 10 to the negative 2, or 0.028, yeah, micrometers. So still makes that number a lot more workable. Good. So we're getting into derived units. This is actually a picture of my mom at, where was this? I think it was in Norway or something. Not Norway. Sweden. I can't remember. The Nobel Prize, the Nobel Museum. Yeah, I think it's in Stockholm, Sweden. Anyways, so this is a unit. This is a cubic meter that she's sitting inside of. So we have some units, they're called derived units. And many volume units are derived units. So any unit of length, when cubed, becomes a unit of volume. So cubic meters, cubic centimeters, cubic millimeters, even something like cubic feet, cubic inches. Those are all units of volume. What changes, though, is if you go from, a length cubed to something like a liter or a milliliter. Liters and milliliters are units of volume, but they are not derived units. You can convert them into derived units, but they are not themselves derived units. So we're talking about some problem solving for math problems now. This is how I see math word problems. If you have 4 pencils and I have 7 apples, how many pancakes will fit on the roof? Purple, because aliens don't wear hats. Yeah, yeah. They can, very often seem like that, and I try to write them as best as possible to leave out any extra words. But yeah. So, and this is why unit conversions become so important, is because there's not a simple formula that applies to every single problem. You can't just say, there's the equation, plug in the numbers, solve it. There's a lot of really determining what that equation is based on the units. And so that's why this unit conversion worksheet is so important. You can learn solving strategies. I'm going to talk about one of them. And many problems can be thought of as, again, unit conversion problems. We're just converting most of the time from one unit to another. We have a few problems that require specific equations, but just a few. So again, we kind of covered this in lab, but units are multiplied, divided, and canceled like any other algebraic quantities, right? So meaning like x, y, right? We can cancel them like we would those variables. And then using those units as a guide to solving problems is called dimensional analysis. And of course, you can find other videos on YouTube explaining dimensional analysis. Sometimes it helps to just hear it explained a different way. A couple keys, though, are always write every number with its associated units. Because if you leave off those units and you're trying to use units as a guide, why make yourself remember them for what that number are, or if you forget and then you'll do the wrong conversion. Yeah, you should always have those associated units. Always include units in your calculations. And don't let units magically appear or disappear in calculations. Right? You can't just multiply two numbers together and then magically say that that is now the units that the question was looking for. It doesn't work like that. You'll get the wrong answer. So for most conversion problems, we're given a quantity, some units, asked to convert it into a quantity, convert that quantity to another unit. So I don't think I ever wrote it out like this, but we have our given unit. That's what the question's giving you. You have then your conversion factor, which is going to be made up of two different types of units. One of those are the units that you're given, or the units that you're trying to remove. And the other one is going to be the unit that your desired unit, right, what you want to convert into. So then the result of multiplying this together is that you get the given units will cancel out, and then you're just left with desired units. So whenever you look at any of your calculations, you should be able to go through the entire conversion and see this unit cancels that unit and replaces it with this one. And then that one cancels with this one and replaces it with that one. And if you can't make that logical chain of units, you probably did the question wrong. The other thing that might happen is that you wrote the numbers in the wrong spots. So conversion factors are constructed from any two quantities known to be equivalent. So I think I did this 3 times last week, so I can't remember which one I did it. I think I showed you guys like I drew out 1 foot on the board, or 12 inches, and then 1 foot with it, right? So those are equivalent units, right? They both describe the same distance. So that's how we make these conversion factors. So this is going to be very similar to the one, or the table of conversions that you had on the unit analysis worksheet. And these are all equivalent quantities, right? So for kilometers, 1 kilometer is 0.6214 miles. You'll notice here that this foot to centimeters, meter to inches, or even meter to yard, they don't have the word exact next to them. The only one here that's exact is 1 inch is 2.54 centimeters. That's because the inch is defined as 2.54 centimeters. That's important when it comes to sig figs. So if you're looking at these, now here, this one is exact. 1 foot is 30.48, but this has been rounded to that 30.48. So there's probably more decimal places after that. So that's why this isn't exact. So this would have 4 sig figs. And these would all have 4 sig figs. But 1 inch to 2.54 centimeters, that's unlimited sig figs. So for these conversion factors, especially going from English to metric units, the 1 is always going to be exact. The other number is the one that has rounding in it. And so you'll use that other number for the number of sig figs. Yep. Okay, so should be review. This should be even fresh on your mind if you've been working on that worksheet. Okay, so if we want to construct a conversion factor relating inches and feet. So how many inches equals how many feet? Oh.
If we have a test, are we going to be given like a sheet that has the conversion?
Yeah. I will give you, well, actually, let me clarify. I will give you the same sheet, the same table that's on the unit analysis worksheet. I will not give you the metric prefixes. You need to learn the metric prefixes. There are definitely some common ones. So if you look through the unit analysis worksheet, figure out which metric prefixes are there. Those are the most common metric prefixes. There's some that don't get used, like a decimeter. Don't use decimeters. Right? Centimeters, millimeters, meters, kilometers. Those are like, for length, the common ones. Yeah, okay, 12, well, I just said it. Yeah, 12 inches, 1 foot. What about inches and centimeters?
1 inch equals 2.54 centimeters?
Yeah, 2.54, 1 inch. All right, so then those are the conversion factors, and you can use those. And we can write this as 2.54 centimeters over 1 inch, or 1 inch over 2.54 centimeters, right? Because those are describing the same length. We can interchange them like that for whatever conversion that we need to do, whether it's going from inches to centimeters or centimeters to inches. Just make sure that, like the 2.54 here, always stays with centimeters. It's never going to be 2.54 inches equals 1 centimeter. That's the other most common mistake. So in solving problems, again, if you're writing out your units with everything, then you can try and look and see if you have that chain of, inches canceling out, that gives us centimeters, centimeters cancels out, that gives us meters, meters cancels out, that gives us kilometers, right? You can do that logical check, and it's really quick to look at and see if you have the correct units. Check whether the magnitude of the answer makes sense. And this one is the kind of thing that it takes a little bit of work to remind yourself to check for that kind of thing. I've already, in another class, I graded some of the unit analysis worksheets. And there's some where they had a conversion factor like 1,000, or it was 1,000 meters equals 1 millimeter. And they used that as one of their conversion factors. And a meter, right, is about a yard. A millimeter is like that, right? So 1,000 meters is not 1 milliliter or 1 millimeter. So when you get your final answer, make sure that, like, okay, if I'm going from like really small units to really big units, I should get a small number, that kind of thing. And it does take some work to get there, right? Because you write down the answer and like, I got it, and you move on. But those double checks will save you, especially on exams. We talked about conversion factors can be inverted because they're equal to 1. All right, this is the thing that I didn't actually cover. So a solution map is a visual outline that shows the strategic route required to solve a problem. And this is like planning out the conversions that you're going to make before you actually go through and start writing any numbers down. So for unit conversion, your solution map is going to focus on units and how to convert from one unit to another. This is especially important if you're doing like multi-step conversions. Like for the single-step ones, you probably don't need this. You can find that factor on a table. So this is kind of what a solution map would look like. For a single step thing, right, if we want to convert from units of inches and we want to get centimeters, we'd write, okay, I'm starting with inches, and then I'm converting to centimeters, and then you can write down the conversion factor that you would use in between. All right, so if this is inches here, then we multiply by that. Inches would cancel out, and we'd be left with centimeters. Or to do the reverse, right, if we had centimeters here, if we multiply by 1 inch over 2.54 centimeters, again, centimeters cancels out. For single step stuff, maybe it can help to just see, like, I'm going from these units to these units and write that out. Definitely, if that helps, then do it. But it can be especially helpful for more complicated problems. So as a general problem-solving strategy, identify the starting point. So, and this comes down to like any word problem, right? If you have any word problem, try and break it down into the important pieces of information. Underline, like, it gives me this number, underline that. And then like write it down in the area where you're gonna work out the problem as, you know, this is given as these units. And then that's, well, yeah, so identify your starting point, identify the end point, right? So what am I given? What am I trying to find? And then this devising a way to get from the starting point to the end point using what is given as well as what you already know or can look up. It's kind of summarizing into one sentence the whole trick to these unit conversion word problems. And to do that, you can use a solution map. And so instead of trying to like piece and string the whole thing together in your head, start writing down some of those steps. And it's okay if you start to write a solution map and realize that you're at a dead end. Just write another one. This is what I said, buy a ream of printer paper, use that as scratch paper, and just don't worry about grabbing another sheet of paper. Right? A ream is like $5, 500 sheets of paper. Cheaper than buying notebooks, although easier to lose. Yeah. So this is, again, sort the information, break it down into smaller pieces that are easier to deal with rather than looking at the whole thing. And pull those pieces out, write those pieces down. Then you can strategize or create your solution map. Then you can solve and actually write out the mathematical calculations that you're going to do. And then you're going to check to see, right, do your units cancel out appropriately? Is your answer in the right magnitude range? All right, so we'll start with an easy one. Okay, so what are we given? Yeah, 56 centimeters. And we're trying to find, yeah, inches. Wow, I just wrote a question mark backwards. Okay, so our solution map then for this, we would start with centimeters. We want to get to inches. And this one, you might have sort of like at least partially memorized this or know that it's going to be a single step conversion. So then our conversion factor that would go in here would be 2.54 centimeters equals 1 inch. Oops. 1 inch. So then, right, we need to write in here, we need to write that conversion factor in the right orientation. So we want to get rid of what units? Centimeters. So that goes on the denominator. And we're going to replace it with inches. And then, again, from our conversion factor here, I'm going to put 1 inch, 2.54 centimeters. And then we can plug in our number that we're starting with. So 2.54, right, if we take the 5.60, 56.0, multiply by 1, and then divide by 2.54. Or you can skip the multiplying by 1. So our answer will be 22.0472. Okay. And then how many sig figs should we have? 3. So 1 inch, inches to centimeters is an exact conversion. So that's going to have unlimited sig figs, but 56.0 only has 3. So it'll be 22.0 inches. 3 sig figs. Now, this is where the rule of thumb comes into play about greater than 10, less than 0. 22.0, I would consider this to be fine. The problem is if you had 20 and it only had 2 sig figs, or if this was supposed to be 1 sig fig, that's why generally if it's greater than 10, it gets into a lot of nuance. If you want to be safe, you can write this as, I will accept here 22.0 inches. If you don't understand why I would accept that and not only the scientific notation, just write it in scientific notation. That's the safe bet. So this will be 2.20 times 10 to the 1 inches. Okay. Right, so both of those have the correct number of sig figs. I want to do something a little more complicated. This will be fine. Okay, so we're given again a number, 5,678 meters. And we want to convert that into kilometers. So what's my solution diagram going to look like? Close. Yes, these are correct things. I'm looking for the solution diagram though. So just like, yeah, right. Starting with, actually I haven't been doing that, but meters to kilometers. So then the conversion factor, which I heard for meters to kilometers. So 1 kilometer is 1,000 meters. And then, we can put this in here. So if we want to get rid of the units of meter, it's going to be 1,000 meters on the bottom, 1 kilometer on top, 5,678 meters. So 5,678 divided by 1,000 will give us 5.678 kilometers. How many sig figs? Yeah, 4. So we can actually just keep that whole number there, and that'll be our answer. Any questions so far? Cool. All right, now for multi-step unit conversions, it'll be the same procedure, but more steps. And so our solution diagram is really what's going to help us get from A to B, and it might take a little more work to figure out what that solution diagram is going to be. So determine a solution map, follow it to solve the problem. So if we want to go from centimeters to feet, again, we're given 194 centimeters, and we want to get that to feet. So our solution diagram is going to start out with centimeters, but what are we going to convert it to first? Yeah, inches, right? We go centimeters to inches, and then from inches, we know we can get to feet. So centimeters to inches, this is going to be 2.54 centimeters, 1 inch. And then this is going to be now we have, at this step in the conversion, right, we're going to have units of inches. So we want to cancel out those units of inches. So this will be 12 inches is 1 foot. And we're starting with 194 centimeters. So you could do step 1, write your answer in here in inches, then go on to do this next step to get your answer in feet, or you can do it all in one go. Right? We don't have to write out that intermediate because we're doing all multiplication. So It's going to be the smallest number of sig figs. And since these are both exact conversions, it's just going to be based on our starting number. So 194 divided by 2.54 divided by 12. Oops. So it's going to be 6.36482 9. There's more than that, but you get the idea. Because we need to round this down to how many? 3. So this will be 6.36 feet. Now, I do want to point out something important here. When you're typing things into your calculator will follow PEMDAS, right? It'll follow the order of operations exactly, even if that's not what you meant. So when I type this into my calculator, I type in 194 divided by 2.54 divided by 12. And that works. That'll give you the answer. What you can't do, and what you might be thinking is, well, this is 194 times 1 divided by 2.54 times 12. So if you wrote out 194 divided by 2.54 times 12, this will do this part first, and then it'll multiply that whole thing by 12. If you want to think about it like this, you need to put parentheses here, because then that'll do this 2.54 times 12, and now it'll divide 194 by the whole answer of that result. I think the easier way, and again, this is for me. If it's easier for you to do it a different way, do it your way, whatever works. But whenever there's division, I just hit divide, right? So this is 194 divided by 2.54, right? Divided by 12. You can just hit divide again and do divide by 12. So this is, well, actually, that's right because it's got the parentheses. All right, so 6.36, that's the answer there. All right, so a recipe calls for 1.2 cups of oil. How many liters of oil is this? So what are we given? Cups, right? 1.2 cups. And we want to find how many liters. So to start this, we're going to start out our, I'll write out cups. All right, we're going to start with cups. We want to convert it to something, and what we want to get to eventually, and I'm just going to write it on the far right here, is liters. Right? So what would be our first step from cups? Quarts. How many cups are in a quart? Is it 8 or 4? I think it's 2 in a pint, and there's 2 pints in a quart. So I think it's 4 cups in a. Do I have a copy of the unit analysis worksheet? I don't. Let's see. How many cups are in a pint?
2 cups in a pint.
Right, yeah, okay. So we can go straight from cups to quarts. That's fine. And then we can go from quarts, because we were given this conversion factor here. We can go from quarts to liters. So what you're trying to do, or I guess we could have gone, this is the tricky thing with unit conversions. There's multiple ways we could have done this, right? If we had the conversion factor for cups to milliliters, we could do that also, and then go from milliliters to liters. Or we could go from cups to pints to quarts to liters. Here, this is a hint, saying 1 liter is this many quarts. So if I give you a very specific conversion factor, it's a hint that it's probably could probably factor into your chain somewhere. Okay, so cups, we can do cups to quarts. And we said that there are 4 cups in a quart. Right? This is why I hate these conversions. I hate English conversions. 'Cause it's 2 pints, 2 cups and a pint.
There's 2 cups and a pint.
And there's 2 pints in a quart.
Yeah.
Okay, 4. So there's 4 cups equals 1 quart. And then to go from quarts to liters, 1 liter equals 1.057 quarts. And this is something that will probably be, especially for longer conversions, you've experienced this, I'm sure, already on the unit analysis worksheet. For longer conversions, it's definitely going to be harder at first, but you'll start to get the feel for different conversion factors. And I like to think of it like a puzzle, right? You're just trying to find the pieces that fit together. And so once you start learning what those pieces are, the pieces don't change. You just need different ones sometimes. And so once you start to learn which pieces fit together, it'll get easier and easier as you practice this. And we're going to continue to do it a lot. Okay, so we're starting with 1.2 cups. How do we get from cups to quarts? What goes on the denominator? 4 cups, quarts on top. And then we want to go from quarts to liters. Quarts on the bottom with a denominator. Then 1 liter on top. And that'll get you there. So 1.2 divided by 4 divided by 1.057. So this is going to be 0.28338. And again, more decimal places after that. But that's more already than we need. So how many sig figs? 2. So 0.28 liters. Ugh, we're not quite going to finish. That's okay.
Can we round the answer, or we don't have to?
What do you mean by, so this is the only acceptable answer here. And that's because, right, this has more sig figs. Right, it's got 4 as I've written it here. But this only has 2 sig figs, or 1.2. So our final answer needs to have 2 sig figs. Yeah. So you could write this one in scientific notation. It didn't because this is, again, outside. So the rule of thumb was less than 10, greater than 0.1. So this is greater than 0.1, so left it. But you could write this as scientific notation. Right? It's the difference between saying like 1 dozen eggs or 12 eggs. Right? It's the same thing. Oh, good. This is a good one. So if we have a running track, right? If you go to the track, measures 1,056 feet per lap. To run 15 kilometers, how many laps should you run? Now we're getting into some real word problem territory. Okay, here's another hint. Per, right? Miles per gallon. That's how many miles you can drive on 1 gallon of gas. So you could write that as miles per gallon. It's a conversion factor, right? Telling you the relationship between gallons of gas, miles you can drive. So here, 1,056 feet per lap. If we were to write out, this would be one of our givens. 1,056 feet equals 1 lap. All right, so another thing that we're given, all right, underline given, 15 kilometers. So if we have 15.0 kilometers, and then what is the question asking us for? Yeah, how many laps? So majority of the time, you want to start with a number that's not a conversion factor. So 1,056 feet per lap, that's a conversion factor. So we're not going to start with that. We're going to start with how many kilometers we want to run. And what we're ultimately trying to do here is convert kilometers into laps. we're just converting units. So if we're starting with 15.0 kilometers, or I guess the other given we had here, right, this is a hint, 1 mile equals 5,280 feet. Man, I should have brought that unit analysis worksheet with me. So I wrote this. All right, and so ultimately we want to get to laps. So look at our first step B here.
Solution map, going from kilometers to miles.
You go kilometers to miles? Yeah, kilometers to miles. That's a conversion that's on that chart, and I think it's 1.602 kilometers equals 1 mile.
1 kilometer is 0.6214 miles.
0.62.
It said 1 km equals 0.6214 miles.
0.6214 miles.
Ah. Yeah. So this is actually, well, okay, I'll do it that way because that's what you have. This is actually the same. If you go 1 mile instead of 1 kilometer, but I'll write it the way that you have it. So 1 kilometer equals 0.6. Yeah, that'll work too. Okay, so we'll go kilometers to miles. And then what should we do next? Because we can't get from miles to laps.
Miles to feet.
Miles to feet. And then from feet, because we have 1,056 feet is 1 lap, we can go from feet to laps. So miles to feet would be 1 mile is 5,280 feet.
If we don't have like the information, can we Google it, like how many miles equals what?
Well, okay, so on an exam, I will give you the table that I want you to use, and you should be able to solve everything using that table, even if that means that there's a few extra steps. In terms of like homework and stuff, you can Google it, but depending on how many sig figs it gives you, because like neither of these are, actually no, this is the only one. This is an exact conversion factor, right? There's going to be more decimal places. But let me solve this real quick because I realize we're a little over now. All right, so we're going to plug in now that we want to get rid of kilometers. So 1 kilometer, 0.6214 miles. And then to go from miles, right, we have units of miles, so 1 mile, 5,280 feet. And then to go from feet to laps, yep, feet goes on the bottom, and it's 1,056 feet is 1 lap. So what starts as, and hopefully this is, what starts as a really sort of confusing problem in the way that it's worded, if you can just pick out what I'm starting with and then just start to build those little bridges, work on it one piece at a time, you can get to the answer without even really understanding how you got to the answer. And sometimes that's okay. Because once you get there, maybe you can realize like, oh, okay, I see how this works now. Yeah. Yeah, so we'll multiply 15 times 6.6214 times 5,280 divided by 10,000 or 1,056, and that'll give us 46.605 laps. We only have 3 sig figs, so 46.6 laps, or 4.66 times 10 to the 1 laps. Cool. Yeah. Yep, we'll get to the rest of this on Wednesday then.